Welcome to the second video of Chapter 3. We're going to talk about least squares, regression lines, and residuals. One big point just for note keeping is that in this section, and whenever we talk about least squares, regression lines, we want to do a y hat, not just a y. And the reason is that hat tells you your equation is from a sample and you use statistics to calculate this equation. It's not some known formula where we know y equals 2x plus 7. It's from a simulation, from data, from sampling. So you always want to put the hat on. Another point is when we do get a least squares regression line, we want to be careful about extrapolation. And the reason is if we have a data set, let's go back to this data set, and I got this equation, I only know that's true for these data points. I don't know if when I go further out, do these data points start going up exponentially? Do they plateau? I don't know what's happening to the data. So if I try to say, hey, what happens at x equals 110, that's outside of my data range. So that would be extrapolation. I could use this equation to say, what is my expected value at 75? That's an acceptable use of using the line to do a prediction. Also, I wouldn't want to say what happens if I got a score of 0 on this stress test, because again, that would be outside of my data range. So if you're doing predictions, it always wants to be within your data range. All right, so let's look at the equation of a least squares regression line. We got y hat equals a plus bx. Now, most of the time, we're going to be doing this from a computer output, from our calculator. Once in a while, you'll be given information and asked to create the least squares regression line. And these two formulas will be on your formula sheet. Well, actually, this one, I believe you should know why. It's the same as y equals mx plus b. They just, in stats, they just use a and b. The other thing to know is that the least squares regression line always goes through the x bar comma y bar point, which hopefully makes sense because if you're doing the best fit line, it should make sense intuitively that your line should go through the average of the x values and the average of the y values. So that point is always on the least squares regression line. Okay, so how would we use this information to mathematically come up with an equation? So you might be given these pieces of information in a question, and you just have to substitute them in. So I can go straight to finding the slope because I know my R value. And then I know my standard deviation of my Y's and my standard deviation of my X's. And I type that into my calculator and I get 0.4005. Then because I know this line goes through X bar, Y bar, I'm going to use my point slope and substitute in. So I'm going to take my Y and make it a Y hat, and then substitute in my X bar, Y bar point. Slope is this. And then I rearrange and I get Y hat equals 0.4005 X plus 0.699. And that would be your least squares regression line from these statistics that you were given. Another thing with the least squares regression line is that it may or may not touch one or none of your points or more than one. We don't know how many actual observation points it'll touch. It doesn't have to touch any to still be a legitimate least squares regression line. And the error between your observed value and your expected value that's on this least squares regression line This is called a residual. It is the error between your observed and your expected. And you should have an equal amount above and below in magnitude. So if you took all your residuals, added them together, you should get 0. And the formula I have written down here for you in words and symbols. So residual equals observed minus predicted, or y minus y hat. And these are the errors from the line to your observed value. And notice, since it's observed minus predicted, if it's above the line, you're going to have a positive residual, and if it's below the line, you have a negative residual. We're going to use these residual plots to help us tell if a least squares regression line is a good fit. And the way you know is if your residual plot is random, it means that a line is a good fit for that data because your points are just bouncing around in a linear fashion, not in a predictable way. Whereas if I had a parabola and I drew a line through it, then I would get a pattern in my residuals. So I have a positive, we'll call that one on the line, negative, 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 and a little positive. So if I were to graph these residuals, I would have positive, 0, negative, more negative, 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 and a little positive. So you can see that residual has a pattern, which means a line's not a good fit for that data. I should look for a different equation. And here is a better picture of a residual plot that has an obvious pattern, and therefore a line is not a good model for this. There is one piece of information you might get from doing simulations in your calculator or from reading a computer output, and that's the standard deviation of the residuals. And what that tells you is, on average, how far are the points away from the line of least squares regression. So it's actually a very useful piece if you're trying to figure out how big of an error you have on average. Okay, so lastly, we're going to do some calculator practice, trying to graph the residuals and also how to list the residuals. And the key before we switch to the calculator is the calculator stores the residuals for the last linear regression you've done. So if you're not sure if the last linear regression is the one you care about the residuals for, run it again, because you might have a previous linear regression stored, and then you won't have any, your residuals won't match what you actually ran, and it'll be a big mess. Okay, so we are going to take out our calculators. And I have written down, this is from the previous video. This is the equation for the least squares regression line of the data that's in stat. So let me bring that up just in case you don't have it in your calculator right now. So we have list 1, list 2, those are our data points. And just to be safe, we're going to run another linear regression. So you go stat calc down to number 4, just enter until you get the results. All right, so by running that again, I just made sure that the residuals in the calculator's memory are the residuals for this set of data. So I can do a couple of things. One is I can take a list and put the residuals in it. So I can go stat. Oh, nope, sorry. I want second stat. And down at the bottom, you will see resid. If I press enter, so L3 equals resid, and if I press enter here for each ordered pair, it'll give me the residuals for each of those. So that is the residuals. If you want to satisfy your curiosity and don't feel like adding those in your head, you could do a one variable statistic on that list. And you will see the sum is essentially 0 for the sum of the residuals. It's to the negative 12th power. All right, so let's say we want to graph the residuals. I'm going to go second y equals to get my stat plot. I'm going to go to the first one. It's already on scatter plot. I still want my x list to be my x values, but my y list is going to be the residuals. So again, I can go second stat to get the list and do resid. And now I can go to graph. And I'm going to want to zoom. And again, with any stat thing, usually the zoom is messed up. So you have to go zoom 9. All right. So you could make the argument that this has a pattern, but there's so few data points that you can't really tell. And so this, in conjunction with the scatter plot of the data, will show you that a line is a good fit for this data. It's just there's so little data here that it's hard to see if there is or is not a pattern. All right, so let's go back to the slides, and we have a couple more things to address. We have R squared now. We talked about R. That's how strong is the correlation. Is it strong, moderate, weak? Then we have R squared, which is the coefficient of determination. And what this does is tells you how much better did your error get from just using a mean as your line. So just saying all the y values should equal y bar. How much better did that error get when I switched to this line here? So going from the red to this blue line, how much better did my error get from all the points? So the R squared calculates that and tells you what percentage it got better. And there's a specific interpretation for this, and this is the fill in the blank I have here. So let's say your R squared equals 0.79. So you would say 79% of the variation in number of, let's say, YouTube followers can be explained by the linear relationship with the number of videos uploaded. I'm pretty sure that would not be a linear relationship or really probably have any correlation. It's the first thing I thought of. So you want to write it in context and then also have the percentage there. So it's good if you can kind of just memorize this at this point, and then hopefully as we do activities, you will get a deeper understanding of what this means. So again, just to reiterate, the R square is telling you if I went from saying all the y values are going to equal y bar no matter what the x value is, and I took that error and compared it to the error of instead using a linear regression line to find the y values and took that error, how much better did that error get? So that's what R squared is telling us. And that is the end of our video.